Welcome back. In this next short segment, we're going to talk about one more physical or physics-based forensic techniques that can use simple linear constraints, and that is lens flare. You've almost certainly seen this either in an image you've taken or in movies, either intentionally or unintentionally. When the camera is facing the light, as you see right here, you see the streaking of light, also called lens flare, that is the result of the way that light enters into the optical train and bounces around that. It's a very uniquely to lens-based systems. This wouldn't happen, for example, in a pinhole camera or a camera obscura, the way we talked about in the background section to this class. And that's going to turn out, although the phenomenon is quite complicated, and the patterns that you see in lens flare are quite complicated, there's a very simple underlying geometric structure. And I don't think it's going to surprise you to learn that that structure is going to be linear in nature. So here is our favorite 3D simulation again. We've got the tiled floor, we've got the crate in the middle, and you can see that I've put a light right here, and you can see that the light is visible. And so lens flare will not manifest itself when the light is behind you or when it's off to the side. It's typically when it's relatively close to the field of view of the camera, so that light can go directly into the camera and then it bounces around and creates two types of patterns that you see here typically. These star patterns where you see the lines emerging from the light source, so I've drawn those with lines here, and then the circular, they don't have to be circular, it will depend a little bit on what the aperture in the camera is. So if you have a hexagonal aperture, those may be hexagonal in shape, but some type of geometric shape. And what you notice here is that, what have I done here? I've drawn lines connecting those star patterns that you saw emerging. And I've drawn circles around those circular lens flare patterns and then fit a line to the center of those circles. And what do you notice? That all of those lines intersect at, well, the projection of the light source. And that's actually pretty cool. It doesn't happen very often, only every once in a while. I've only used this once ever since I've made this observation. But when it happens, it's a nice little trick that you can use to analyze lens flare. And so here's an example of that. All right, out in a snowy mountaintop, and there seems to be a post office box right there. You can see the light, the sun, obviously, right here in the corner, and you can see two patterns of lens flare, one streaking across the image this way, and one streaking this way. And in this particular case, you can't really see the linear patterns, but you can clearly see the circular patterns going in multiple directions, and you can, at least without even doing the data fitting, see that they converge to roughly that point right there where the sun is. Now, the projection of the light source, we now have two ways of determining what that is. Lens flare, but don't forget, we also have shadows. So what the shadow constrains is also the projection of the light source. So let's see what happens when you apply that analysis here. So I've drawn a line along the top here, and then along the diagonal that connects the center of those circles of the lens flare. I just fit a couple of the circles. You don't have to do all of them, the ones that are particularly well defined. And those two lines intersect right there. That looks about right for the projection of the light source. Notice that I've expanded the boundaries of the image plane so I can see where it is. And now notice what I've done with the shadow of the post box. I've drawn a wedge-shaped constraint that takes the tip of the shadow and says, well, that must be somewhere near the top of the mailbox. I could have expanded that downward. It wouldn't have actually made any difference. And notice here that this region here, that of course extends to infinity, does not include that point right there. And now we have an inconsistency between the lighting that the lens flare tells us where the light is and where the shadow is. So you can think of this as almost like an additional, when it's available, type of lighting constraint, the same type of constraint that the shadow gives you. And if you wanted to, you could have made these a little bit fatter. You could have made them cones instead of specific lines. It would have worked just fine. So it's a cute little observation that when it's in the image, and it is rare, it happens every once in a while, you can use that as a constraint for the projection of the light source in the same way that we used cast shadows. Okay, so now we've seen vanishing points, vanishing lines. We've seen reflections, we've seen shadows, cast and attached, and we've seen the not very common but sometimes occurring lens flare, all can be described with these simple linear constraints, either straight lines or those wedge-shaped constraints to deal with a little bit of uncertainty in the image. And you can see why these are very powerful techniques. You simply apply them to an image, and you can reason about the 3D physical world and what was happening out there, and whether those are consistent or have been altered due to some type of manipulation. Now, obviously, if the forger knows what you're doing, they can do the same analysis and fix what you're doing. That's going to be true of every forensic technique. We have to come to grips with that, and that's just the way it is. Now, I've mentioned this a few times, and I'm going to mention it one more time because the next segment is going to dive into this, is that what's next is we're going to take a little bit of a break from doing actual forensic analysis. We're going to talk about the human visual system. And we're going to talk about how good is the human visual system at detecting inconsistencies in shadows, reflections, and projective geometry, or perspective projection. And the reason we want to do that again is twofold. One is we have to understand our limitations. As forensic analysts, it's incredibly important to know when we look at something, what are we good at, what are we not good at, and of course knowing what our forger is good at and not good at also benefits us. So we're going to take a little bit of a step off in the next segment. We're going to talk about some psychophysical experiments where we looked at the accuracy of people analyzing images to determine if they're consistent or not in terms of projective geometry, shadows, and reflections. We're going to see where we do well, where we don't do well, and then we'll continue on with some new forensic techniques and analysis. All right, we'll see you in a little bit.